Right now, somewhere behind the sun where no telescope on Earth can see it, an object that has no business being in our solar system is making its closest approach to our star. It's traveling at speeds that defy the gravitational rules that govern everything else out here. It came from somewhere beyond the reach of the sun's influence, from the space between stars. And tomorrow, October 30th, to be precise, it will swing past the sun at a distance of 125 million miles before continuing its journey back into the interstellar void. The object is called 3I Atlas, and it's only the third interstellar visitor we've ever detected passing through our cosmic neighborhood. And here's the thing that has scientists scrambling to point every available instrument at it. We have no idea what's going to happen next. Let me show you what I mean. Perihelion, that's the technical term for the closest point any object gets to the sun, isn't just another data point for astronomers to log in their notebooks. For comets, especially comets on the kind of wild, eccentric trajectories that bring them screaming in from the outer reaches of space, perihelion is showtime. It's the moment when the sun's heat becomes intense enough to trigger a transformation that turns what might look like a dirty snowball into something magnificent and terrifying. The ices locked in the comet's surface begin to sublimate, going directly from solid to gas without passing through liquid. This outgassing creates a glowing cloud called a coma that can grow larger than Jupiter. The solar wind, that constant stream of charged particles flowing out from the sun, strips material away from the comet and stretches it into two distinct tails, one made of dust particles reflecting sunlight, another made of ionized gas glowing with its own eerie light. The comet brightens, it becomes visible. It puts on a show. At least that's what's supposed to happen. That's what happens to our comets, the ones that were born in our solar system billions of years ago. But 3I Atlas? It's not one of ours. It came from somewhere else, somewhere we've never been and may never reach. And the question everyone's asking is, will it behave like our comets, or will it do something we've never seen before? The discovery itself reads like the opening chapter of a cosmic detective story. 3I Atlas was first spotted earlier this year by the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, a network of telescopes in Hawaii designed to scan the skies for potentially hazardous asteroids. The designation 3I tells you everything you need to know about how rare this object is. It means this is only the third confirmed interstellar object we've detected. The first, 1I Oumuamua, caused an international sensation when it passed through in 2017 with its bizarre cigar-like shape and unexplained acceleration. The second, 2I Borisov, arrived in 2019 and behaved more like what we expect from comets, with visible outgassing and a traditional coma. Now we have 3I Atlas, and from the moment astronomers calculated its trajectory, they knew they were looking at something special. The orbital analysis showed hyperbolic velocity, meaning this object is moving too fast for the sun's gravity to capture it. It's not orbiting our star. It's just passing through like a traveler stopping at a rest area on an infinitely long highway. Its path through our solar system is more like a parabola than an ellipse, and when it's done with its close encounter with the sun, it will head back out into the darkness between stars, never to return. For context, this is extraordinarily rare. Most comets we study were born in the Oort cloud or the Kuiper belt, distant regions of our own solar system, and they're bound to the sun by gravity, doomed to orbit forever or until something catastrophic happens. But interstellar objects like 3I Atlas are refugees from other stellar systems, ejected by gravitational interactions billions of years ago and wandering the galaxy ever since. Think about what that means. This comet might have formed around a star we can see in our night sky, or it might come from a star so distant that its light hasn't reached us yet. It could be older than our solar system, or it could have been kicked out of its birth system just yesterday in cosmic terms. Let's back up to what happened before we lost sight of it. Throughout September, astronomers around the world were tracking 3I Atlas with increasing excitement. The comet was getting brighter as it approached the Sun, exactly as predicted. Telescopes on Earth and in orbit were gathering data, spectroscopic measurements that revealed its chemical composition, photometric observations that tracked changes in brightness, imaging that showed the development of its coma and tails. Everything was proceeding according to plan, and then, at the end of September, 3I Atlas moved into what's called solar conjunction. This is the astronomical equivalent of someone walking behind a pillar, just as you're trying to photograph them. From Earth's perspective, the comet moved into the same part of the sky as the Sun, lost in the glare of our star's overwhelming brightness. It's not that the comet stopped existing or that something dramatic happened to it. It's simply that we can't see it anymore from our vantage point. The Sun is roughly 400,000 times brighter than the full moon, and trying to spot a comet when it's in the same direction as the Sun is like trying to see a candle flame when someone's shining a stadium spotlight in your eyes. This isn't an unusual occurrence. Planets and comets pass behind the Sun all the time, but the timing couldn't be worse. The period around perihelion is when comets are supposed to be at their most active, when the show is supposed to reach its crescendo. And for 3I Atlas, that moment is happening right now tomorrow, October 30th, while we're effectively blind. The comet won't emerge from behind the Sun until late November or early December, when it will reappear in Earth's morning sky. By then it will be moving away from the Sun, cooling down, potentially becoming less active. We're missing the main event. This is maddening for astronomers who have been planning observations for months. The Hubble Space Telescope, perched in low Earth orbit, can't point anywhere near the Sun without risking damage to its sensitive instruments. The James Webb Space Telescope, stationed at the L2 Lagrange point, a gravitationally stable position on the opposite side of Earth from the Sun, has the same limitation. Ground-based observatories are constrained by the simple fact that you can't observe something when it's behind the Sun during daylight, and even before dawn or after dusk. The comet is too close to the horizon, buried in the atmospheric murk and solar glare. But here's where it gets interesting. We're not entirely blind. Yes, Earth-based assets are out of the game for now, but we've spent the last several decades doing something remarkable. We've scattered a fleet of robotic explorers throughout the solar system. And some of those spacecraft, quite a few of them actually, have viewing angles that are very different from ours. Remember, space is three-dimensional. And just because we can't see the comet from Earth doesn't mean it's invisible from everywhere else. The flotilla of missions currently active at Mars, for instance, has a spectacular view of the hemisphere of the solar system, where 3I Atlas is currently rounding the Sun. These aren't telescopes designed for comet observation, mind you. They're rovers and orbiters built to study Mars, to photograph its surface, to analyze its atmosphere, to search for signs of past or present life. But they have cameras, they have instruments, and their handlers back on Earth can, with some creative repurposing of mission time, point those cameras at an interstellar visitor. The Mars missions had an even better opportunity earlier this month. On October 3rd, 3I Atlas made its closest approach to the red planet, passing within 0.19 astronomical units. That's about 17.6 million miles, or 28.4 million kilometers. To put that in perspective, that's closer than Mars ever gets to Earth, though still far enough that the comet would have appeared as a point of light, rather than a resolved object. But for spacecraft equipped with sensitive cameras and spectrographs, that's close enough to gather valuable data about the comet's composition, its activity level, how much dust and gas it's producing. The Mars fleet includes NASA's Perseverance and Curiosity rovers on the surface. though their ability to observe the comet would have been limited by the Martian atmosphere and their surface perspective. More importantly, there are several orbiters: NASA's MAVEN, Mars Reconnaissance Orbiter, and Mars Odyssey, the European Space Agency's Mars Express and Trace Gas Orbiter, and the United Arab Emirates HOPE probe. That's a considerable amount of observational firepower, and the mission teams have been coordinating efforts to capture as much data as possible. Here's where things get really strange. We're not just talking about the Mars missions. NASA's Psyche spacecraft, currently on its way to a metal-rich asteroid between Mars and Jupiter, has been tracking 3I Atlas during its journey. The Lucy mission, designed to explore Jupiter's Trojan asteroids, those groups of space rocks that share Jupiter's orbit, clustering around gravitationally stable points ahead of and behind the giant planet, also has the Comet in its sights. And then there's JUICE, the European Space Agency's Jupiter Icy Moons Explorer, which recently performed a gravitational slingshot maneuver around Venus as part of its complex trajectory to the Jovian system. JUICE happens to be heading in a direction that brings it relatively close to 3I Atlas's path. In fact, of all our spacecraft, JUICE probably has the best viewing geometry for observing the comet around perihelion. But, and this is where the universe demonstrates its sense of irony, JUICE has a problem. During this phase of its mission, the spacecraft is oriented with its primary high-gain antenna pointed toward the Sun, using it as a heat shield to protect its sensitive scientific instruments from solar radiation. This is a necessary precaution. The spacecraft wasn't designed to be this close to the Sun for extended periods, and without that protection, some of its delicate components could be damaged. But that orientation means JUICE can't communicate with Earth. The antenna that's supposed to transmit data back home is busy being a sunshade. The spacecraft is almost certainly observing 3I Atlas right now, recording images and measurements, but all that data is being stored on board. We won't receive it until February 2026, when JUICE reorients itself and reopens communications with Earth. Think about that. We have a spacecraft in the perfect position to watch an interstellar comet at perihelion, and we can't see what it's seeing for another 4 months. It's like someone describing an incredible view to you over a phone that keeps cutting out, and they're saying, "I'll send you the photos later." And you're just standing there, desperate to see what they're seeing. Let me shift gears and talk about what makes this whole situation so scientifically valuable. Because it's not just about getting pretty pictures of a comet. The study of interstellar objects is one of the most exciting frontiers in planetary science right now, and we've only just begun to scratch the surface. Before 2017, interstellar objects were purely theoretical. We knew they had to exist. Gravitational simulations of planetary system formation showed that countless billions of comets, asteroids, and larger bodies must have been ejected from their home systems over the billions of years since the galaxy formed. We calculated that there should be more free-floating interstellar objects in the Milky Way than there are stars, but detecting them was another matter entirely. These objects are small, dark, and moving rapidly through space. Finding one as it passes through our solar system is like trying to spot a specific grain of sand thrown across a football stadium. The odds are absurdly low, yet we've now found 3 in 8 years. Stop and consider that. Either we've been incredibly lucky, or there are far more of these interstellar wanderers out there than we thought. Some astronomers are now suggesting that the estimates were too conservative, that interstellar objects might pass through the inner solar system once or twice a year, and we're only now building survey systems powerful enough to detect them. The Vera C. Rubin Observatory, currently under construction in Chile, is expected to discover dozens or even hundreds of interstellar objects once it becomes operational, revolutionizing our understanding of what's floating between the stars. Let's talk about what we do know. And trust me, what we know is already breaking every rule. Each of the 3 confirmed interstellar objects has been dramatically different from the others, suggesting we're sampling from an incredibly diverse population. Oumuamua, the first detected, was unlike anything we'd ever seen. It was highly elongated, possibly 10 times longer than it was wide, tumbling through space like a cosmic football. Its surface was reddish, likely from eons of exposure to cosmic radiation. And here's what really got everyone's attention: it was accelerating, not slowing down, which is what you'd expect from an object moving away from the sun after a close pass. It was speeding up as if something was pushing it. The most straightforward explanation was that it was outgassing, releasing jets of vapor that acted like tiny rocket engines. But here's the problem. Nobody could detect any coma, any dust tail, any of the usual signs of outgassing. Some researchers proposed that it might be venting pure hydrogen, which would be invisible to our telescopes. Others suggested more exotic explanations. One controversial paper even proposed that Oumuamua might be an artificial object, a light sail from an alien civilization. Most scientists dismissed that idea, but the fact that it was even discussed in peer-reviewed journals tells you how weird Oumuamua's behavior was. Then came 2I Borisov in 2019, and it was refreshingly normal. It looked like a comet. It acted like a comet. It had a prominent coma and dual tails. Its composition, analyzed through spectroscopy, was similar to comets from our own Kuiper belt, suggesting that comet formation might be similar across different stellar systems. Astronomers breathed a sigh of relief. Maybe Oumuamua was the anomaly, and most interstellar objects would be familiar, just visitors from neighborhoods that happen to be light years away rather than billions of miles. And now we have 3I Atlas, and we're back to being confused. The early observations showed behavior that was more comet-like than Oumuamua, but with some perplexing quirks. The comet's brightness increased as it approached the sun, which is expected, but the rate of brightening didn't quite follow the models. Spectroscopic analysis revealed the presence of water vapor and carbon-based molecules, standard comet stuff, but also some spectral lines that didn't fit neatly into expected categories. One research team reported detecting emission lines consistent with organic compounds more complex than those typically seen in solar system comets, though this finding is still being debated. The comet's nucleus, the solid core beneath all the gas and dust, appears to be relatively small, perhaps a few kilometers across at most, but estimates vary wildly depending on how much of its brightness comes from reflected sunlight versus outgassing. Its coma developed rapidly once it crossed inside Jupiter's orbit, suggesting a surface rich in volatile ices. But the structure of that coma has been asymmetric in ways that are difficult to explain. Some images showed a fan-like pattern in the dust distribution, implying that material was being ejected preferentially from certain regions of the nucleus, possibly from active vents on a rotating body. But the rotation rate required to explain those patterns doesn't match the light curve variations that would indicate how fast the nucleus is spinning. That word asymmetric is doing a lot of work there. It suggests something complex is happening on the comet's surface, something that doesn't match the simple model of a uniformly heated snowball melting in the sun. Before you dismiss this as just another comet with some unusual features, consider what perihelion means for an interstellar object. Our solar system comets have been doing this for billions of years. If they're on short-period orbits, swinging past the sun every few decades or centuries, they've been baked and frozen and baked again countless times. Their surfaces have developed thick crusts of refractory material, substances that don't easily vaporize, which modulate how they respond to solar heating. We understand their behavior because we've watched them over multiple orbits. We can predict when and how they'll brighten, when they'll develop tails, when they might fragment or undergo outbursts. But 3I Atlas, this might be its first time getting this close to any star in millions or even billions of years. Depending on where it came from and what happened to eject it from its home system, this comet might have spent the vast majority of its existence in the cold of interstellar space, where temperatures hover just a few degrees above absolute zero. If that's the case, its surface might be pristine, covered in exotic ices that have never been heated before. We have no idea how those ices will respond to the sun's warmth. Will they sublimate smoothly, or will they explode violently? Will the comet brighten dramatically, or will it have already developed a protective crust during its passage through the outer solar system? The answer is unfolding right now tomorrow, while we're stuck watching from the wrong angle or waiting months to receive data from the spacecraft that can see it. Now, about that timing issue, the fact that 3I Atlas is passing through perihelion while it's in solar conjunction isn't just frustrating from a scientific standpoint. It's raising some interesting questions about the nature of these interstellar visits. Here's the thing: solar conjunctions are inevitable. From Earth's perspective, any object in the solar system will eventually pass behind the sun as it moves along its orbit or trajectory. For planets and asteroids and comets that orbit the sun, we can predict these conjunctions far in advance and plan our observations accordingly. If we miss an event because of solar conjunction, we can just wait for the next orbit. But for interstellar objects, there is no next time. They pass through once and they're gone forever. The trajectories of these objects are determined by where they came from in the galaxy and how their path happened to intersect with our solar system. It's entirely random. And yet, of the 3 interstellar objects we've detected, 2 of them, Oumuamua and now 3I Atlas, had perihelion passages that coincided with periods when Earth-based observation was difficult. Oumuamua was discovered on its way out of the solar system after it had already rounded the sun, and its trajectory took it through the plane of the solar system at a steep angle that made it visible for only a short window. 3. Atlas is hidden behind the sun during its most active period. Is this just bad luck? Probably, but it's led to some tongue-in-cheek speculation among astronomers that if there were alien civilizations deliberately sending probes to study our solar system, these would be exactly the kinds of trajectories they'd choose. Paths that let them make a close pass by the sun and the inner planets while remaining hidden from Earth-based observation during the most critical phase. Nobody's seriously suggesting this is what's happening with 3I Atlas, but the coincidence is irritating enough that it comes up in conversations. Let's bring this back to the spacecraft observations, because that's where we're going to get our perihelion data from, at least for now. The Mars missions are particularly valuable for another reason beyond their viewing angle. They give us a baseline for comparing the comet at different distances from the sun. When 3I Atlas passed Mars on October 3rd, it was still several weeks away from perihelion, still approaching the sun and heating up. The data gathered by the Mars orbiters captured the comet in a specific state of activity. Now, as 3I Atlas reaches perihelion on October 30th, the Psyche and Lucy spacecraft, and especially JUICE, are observing it at peak solar heating. When 3I Atlas emerges from solar conjunction in late November or December and becomes visible from Earth again, we'll be seeing it as it cools down and moves back toward the outer solar system. By combining all these observations, astronomers will be able to piece together a complete picture of how the comet's activity evolved throughout its perihelion passage. That's actually unprecedented. For Oumuamua, we only got observations after it had already passed the sun. For 2I Borisov, we were able to track it for several months, but we didn't have this kind of distributed observation network providing multiple simultaneous viewing angles. With 3I Atlas, even though Earth-based telescopes are blocked by the sun, we're getting a 3-dimensional perspective on the comet's behavior. Different spacecraft see different parts of the coma and tails. They sample the solar wind at different locations, which helps determine how the comet's ion tail is being shaped by solar particles. They measure the comet's brightness from different angles, which can reveal information about how light is being scattered by dust particles of different sizes. Think about what that means for our understanding of cometary physics. Comets are notoriously unpredictable. They undergo sudden outbursts where their brightness increases dramatically for a few hours or days before settling back down. They fragment, splitting into multiple pieces that then follow separate trajectories. They develop jets and plumes that can change the comet's rotation or alter its trajectory. All of this behavior is driven by processes happening on and just below the surface of the comet's nucleus, which we can't observe directly. We can only see the results, the gas and dust streaming away into space. Having multiple spacecraft observing simultaneously means that when something unexpected happens, and with comets, something unexpected always happens, we can triangulate. We can figure out which part of the comet is responsible for a particular feature in the coma or tail. We can measure how quickly material is flowing away from the nucleus. We can track how the structure of the tails changes over time as the comet moves relative to the sun and the solar wind. This is the kind of data that lets us test theoretical models and refine our understanding of what actually happens when a comet's ices sublimate. Actually, let me correct that. The real value isn't just in understanding comets, it's in understanding the building blocks of planetary systems. Comets are time capsules. They're made from material that condensed in the outer regions of a protoplanetary disk billions of years ago, when a star was first forming and the cloud of gas and dust around it was coalescing into planets. Because comets spend most of their time in the cold outer reaches of a solar system, their ices and organic molecules remain largely unchanged, preserved in a deep freeze. When we study comets from our solar system, we're learning about the conditions that existed when the Sun and Earth and all the planets were forming 4.6 billion years ago. But when we study an interstellar comet like 3I Atlas, we're learning about the conditions in a different stellar system, one that might have formed at a different time, from a cloud with a different chemical composition in a different region of the galaxy. By comparing interstellar comets to our own, we can start to answer fundamental questions. Are comets the same everywhere? Do different types of stars produce different types of comets? Are the organic molecules and ices that make up comets universal? Or does each planetary system develop its own unique chemistry? These questions have implications far beyond planetary science. If we want to understand how common life might be in the universe, we need to know whether the chemical building blocks of life, complex organic molecules, liquid water, sources of energy, are rare accidents that happened here and nowhere else, or whether they're inevitable consequences of star and planet formation that happen everywhere. One school of thought suggests that interstellar objects might actually be more important for understanding planetary system evolution than we ever realized. The current model of how planetary systems form involves a lot of violence. Gravitational interactions between growing planets and the remaining disk of material lead to chaos. Objects are thrown inward toward the star, where they might collide with planets or be consumed by the star itself. Other objects are thrown outward, gaining enough velocity to escape the star's gravity entirely and become interstellar wanderers. The ratio of objects thrown inward versus outward depends on the architecture of the planetary system, particularly on where the giant planets form and how they migrate. By studying the population of interstellar objects, how many there are, what types of objects they are, what their compositions tell us, we can work backward to infer what kinds of planetary systems are most common in the galaxy. If most interstellar objects turn out to be icy comets like 3I Atlas and 2I Borisov, that tells us something different than if most are rocky asteroids or bizarre elongated objects like Oumuamua. Early estimates, based on the detection rate of interstellar objects and the sensitivity of current survey telescopes, suggest there might be one interstellar object larger than 200 meters in diameter inside Neptune's orbit at any given time. That's far more than theoretical models predicted just a decade ago. If those estimates hold up, it means planetary systems are even more violent and chaotic than we thought, ejecting a larger fraction of their material into interstellar space. Another school suggests that we need to think about interstellar objects not as exiles from their home systems, but as potential vectors for transporting material between stellar systems. This gets into the realm of panspermia, the hypothesis that life, or at least the chemical precursors to life, might spread between planets or even between star systems via natural processes. If an interstellar comet rich in organic molecules and water ice were to impact a planet, it would deliver those molecules to the planet's surface. If conditions were right, those molecules might contribute to the emergence of life. This isn't science fiction. We know that impacts played a crucial role in delivering water and organics to the early Earth. The question is whether interstellar delivery is significant compared to locally sourced material. If interstellar objects are as common as the new estimates suggest, and if they commonly contain the kinds of complex organics that some researchers think they've detected in 3I Atlas, then the answer might be yes. Every planetary system in the galaxy might be regularly peppered with material from other systems, creating a kind of chemical mixing that homogenizes the galaxy's organic chemistry. If that's true, then the emergence of life might be even more likely than we thought because planets aren't starting from scratch. They're receiving care packages of prebiotic molecules from across the galaxy. But there's a third possibility, one that's more controversial, but that deserves attention given how strange Oumuamua turned out to be. Some researchers have pointed out that our sample size is embarrassingly small. 3 objects. That's not enough to draw statistically meaningful conclusions about anything. And yet, those 3 objects have been wildly different from each other. Oumuamua was probably elongated, possibly by a factor of 10-1, which is far more extreme than anything we've seen in our solar system. Its acceleration remains unexplained, with hypotheses ranging from hydrogen outgassing to thermal re-radiation effects to exotic ices that we've never encountered. 2I Borisov looked like a normal comet, but was enriched in carbon monoxide to a degree rarely seen in solar system comets, suggesting it formed in a colder environment than most of our comets. And now 3I Atlas, with its asymmetric coma and unusual spectral features, and the fact that it's passing through perihelion in a way that makes it hard to observe. The diversity is striking. If you randomly selected 3 comets from our solar system, they'd be broadly similar in most respects. But these 3 interstellar objects? They're all over the place. One interpretation is that this diversity is real, that the interstellar object population includes a much wider range of body types than our solar system does. Another interpretation is that we're experiencing selection bias. We're only detecting the weird ones, because they're unusual enough to catch our attention. A third interpretation, the controversial one, is that we don't actually know what we're looking at. Maybe some of these objects aren't natural at all. Before you dismiss this as fringe science, consider that the people making these arguments aren't cranks. They're respected astronomers from major institutions who are simply following the data where it leads. The argument isn't that 3I Atlas is definitely artificial. There's no evidence for that. The argument is that we shouldn't rule out any possibilities when we're dealing with a phenomenon we've only just started to study, and that has already surprised us multiple times. Most scientists push back hard against the artificial object hypothesis, and for good reason. Extraordinary claims require extraordinary evidence, and so far nothing about the interstellar objects we've detected requires an artificial explanation. Everything can be explained, with varying degrees of difficulty using natural processes. The elongation of Oumuamua might be unusual, but we've seen elongated asteroids before, and it's plausible that collisional fragments or bodies that formed through gravitational collapse and then got stretched during a close encounter with a planet could take on such shapes. The acceleration could be explained by outgassing that we couldn't detect because it was composed of molecules that don't show up well in our spectra. Borisov's carbon monoxide enrichment just means it formed farther from its parent star than most of our comets formed from the Sun. And 3I Atlas's quirks? We won't even know the full extent of those quirks until we get all the data from the spacecraft observations and from Earth-based telescopes once the comet emerges from solar conjunction. Jumping to artificial explanations at this point would be premature at best. But the debate itself is healthy. It forces the scientific community to question assumptions, to rigorously test hypotheses, to consider alternatives. And it raises a deeper question. If we ever do detect an artificial interstellar object, how would we recognize it? What would be the signatures that would unambiguously distinguish a probe or a spacecraft from a natural body? These are questions that SETI researchers, scientists searching for extraterrestrial intelligence, have been thinking about for decades, but they've mostly focused on radio signals or optical beacons. The possibility of detecting physical artifacts, especially ones that are just passing through our solar system rather than being deliberately sent to us, is a relatively new area of consideration. The next critical window is December 20,000, December 2020. That's when 3I Atlas will emerge from behind the sun and become visible again from Earth. The comet will be in the morning sky, observable before dawn from most latitudes. By then, it will be cooling down, having passed perihelion and begun its journey back out of the inner solar system. Astronomers are planning an intensive observing campaign. Every major telescope that can point at the comet will be assigned time to gather data. Spectrographs will analyze the composition of the coma and tails in detail, looking for unusual molecules or isotopic ratios that might reveal information about where the comet formed. Photometric monitoring will track how the comet's brightness changes over time, looking for outbursts or sudden changes that might indicate fragmentation. Polarimetry measurements will characterize the dust particles being ejected from the nucleus, revealing their size distribution and composition. If the comet is still active enough to produce a strong ion tail, spacecraft in the solar wind can measure how the comet is interacting with the stream of particles from the sun. The goal is to gather as complete a dataset as possible before the comet fades from view. By mid-2026, 3I Atlas will be beyond the orbit of Jupiter, too faint for most telescopes to detect, and it will be lost to us forever, another interstellar traveler continuing its billion-year journey through the galaxy. The data we collect between now and then will have to last us for as long as we want to study this object. And there will be data to collect before December, even if we can't see the comet from Earth. Remember JUICE, the spacecraft that's been observing 3I Atlas during perihelion but can't communicate with Earth because its antenna is busy being a heat shield? In February 2026, JUICE will reorient itself and begin transmitting its stored observations back to the ground. Those observations are going to be critical. JUICE carries a suite of scientific instruments designed to study Jupiter's moons, but several of them can be repurposed for comet observations. The spacecraft's visible and infrared spectrometer can analyze the composition of the coma. Its particle and plasma instruments can measure the interaction between the comet and the solar wind. Its magnetometer can detect any magnetic fields, which would be unexpected for a comet but would provide valuable information if they're there. Most importantly, JUICE had a better viewing angle than any other platform during perihelion. While Mars missions and Psyche and Lucy were seeing the comet from the side, so to speak, JUICE was positioned to see it nearly head-on as it rounded the sun. This perspective will reveal details about the structure of the coma and tails that aren't visible from other angles. If the comet underwent any major outbursts or sudden changes in activity around perihelion, and comets often do, JUICE will have recorded them. The data won't be available immediately, even after communications are re-established. Transmitting images and spectra from deep space takes time, especially when the spacecraft is far from Earth, and the data rate is limited. Mission scientists will have to prioritize which observations to downlink first. But by mid-2026, we should have a comprehensive view of what 3I Atlas did during its closest approach to the Sun. For context, compare this to what happened with previous interstellar objects. When Oumuamua was discovered in October 2017, it had already passed perihelion back in September, and was on its way out of the solar system. Astronomers had roughly 2 months to observe it before it faded from view, and they used every available telescope to gather as much data as possible. But they were limited by the fact that they could only see Oumuamua from Earth and from Earth orbit. There were no spacecraft in position to get a different perspective. By the time anyone realized what they were looking at and how important it was, the object was already millions of miles away and receding fast. With 2I Borisov, we had more time. It was discovered in August 2019, several months before its perihelion in December, and it remained visible for nearly a year as it passed through the inner solar system. This longer observing window allowed for more detailed studies, but again we were limited to Earth-based and near-Earth observations. No spacecraft were in position to get close-up views. With 3I Atlas, we're in a better situation in some ways and a worse situation in others. The solar conjunction means we're missing the perihelion passage from Earth, which is frustrating. But the distributed network of spacecraft means we're getting observations from multiple vantage points, which is unprecedented. The trade-off might actually be worth it. A comet observed from Earth alone, even at perihelion, gives you a single perspective. A comet observed from multiple spacecraft scattered across the inner solar system gives you a three-dimensional view of how the comet's coma and tails are structured and how they evolve in response to changing solar radiation and solar wind conditions. This is the kind of data that can distinguish between competing theoretical models, the kind of data that advances the field, rather than just adding another object to the catalog. Speculation time. What's going to happen to 3I Atlas after it leaves our solar system? It's going to continue on its trajectory through the galaxy, traveling at roughly 33 kilometers per second relative to the local standard of rest. That's the average velocity of stars in our region of the galaxy. At that speed, the comet will cover a light year in about 9,000 years. The nearest star system to us, Alpha Centauri, is about 4.4 light years away. So if 3I Atlas happened to be heading in that direction, which it's not, it would arrive in roughly 40,000 years. But space is vast and mostly empty, and the odds of 3I Atlas having a close encounter with another star system are vanishingly small. It might wander the galaxy for millions or billions of years without ever entering another planetary system, or it might pass through another system, perhaps providing alien astronomers with the same kind of excitement and frustration it's giving us. Imagine that. Somewhere out there, maybe a few light years away, maybe dozens or hundreds of light years away, there might be astronomers who watched 3I Atlas leave their stellar neighborhood, who observed it as it accelerated away under the gravitational influence of a giant planet or a close stellar encounter, who wondered where it would go and what it would find. They have no way of knowing it passed through our solar system. They'll never see the data we collect, and we'll never know where it came from, what star it orbited, what kinds of planets might exist in that distant system. This is one of the melancholy realities of studying interstellar objects. Every one of them represents a connection to a place we'll likely never reach, a sample from a planetary system we can study only indirectly through this one visitor. You have to read between the lines in some of the recent papers on 3I Atlas, because there are hints that astronomers are seeing things they don't quite know how to interpret yet. One preprint, a paper that's been submitted to a journal but not yet peer-reviewed, mentions anomalous emission features in the spectra without elaborating on what those features might be. Another paper discusses temporal variations in coma morphology that are inconsistent with simple rotation models, but doesn't provide enough detail to understand what's actually happening. This is typical for early-stage research on a new object. Scientists are cautious about making bold claims before they've thoroughly analyzed the data and ruled out instrumental artifacts or alternative explanations. But it suggests that 3I Atlas has some surprises in store, things that won't become clear until all the observations are collected and the full analysis is published. Researchers who've glimpsed them are tight-lipped. Not because they're hiding anything, But because in science, you don't go public with a finding until you're certain it's real and you understand what it means. Careers have been derailed by premature announcements of discoveries that turned out to be errors or misinterpretations. So the community waits, and those of us on the outside read the published papers and the conference abstracts, looking for clues about what might be coming. Here's another piece of the puzzle that deserves attention. The trajectory of 3I Atlas, when traced backward, suggests it came from the general direction of the constellation Perseus. Tracing the paths of interstellar objects backward through the galaxy is complicated by the fact that stars move. Gravitational influences from nearby stars perturb trajectories, and our own knowledge of the galaxy's gravitational potential is imperfect. But the best estimates suggest 3I Atlas might have been ejected from its home system sometime in the past few million years, and it's been traveling through interstellar space ever since. That's a geological eye blink, cosmically speaking. If the comet formed billions of years ago when its parent star was young, it spent most of its existence in a distant orbit around that star, only to be kicked out relatively recently by some gravitational interaction. Maybe a passing star, maybe a rogue planet, maybe a reshuffling of the architecture of its planetary system. And now, just a few million years later, it's passing through our system, and we happen to be at the right stage of technological development to detect it and study it. The coincidence is staggering. For most of human history, 3I Atlas could have passed through the solar system, and we would have had no idea. Even a century ago, our telescopes weren't sensitive enough to spot something like this unless it happened to become spectacularly bright, which most comets don't. We're living in a brief window of time, cosmically speaking, when we're just barely capable of detecting these objects and just starting to develop the tools to study them properly. In another century, we might have telescopes on the moon or in deep space, or fleets of interceptor spacecraft that can be dispatched on fast trajectories to rendezvous with interstellar objects and study them up close. But right now we're in this awkward adolescent phase where we can see these objects and realize their importance, but we're limited in what we can learn from them. There's a broader context here about the evolution of astronomy as a science. For most of its history, astronomy was a passive discipline. You looked at the sky, you recorded what you saw, and you tried to make sense of it. You couldn't touch the objects you were studying. You couldn't experiment on them. You could only observe. That started to change in the 20th century with the advent of space exploration. Suddenly, we could send spacecraft to other planets, land on the moon, bring back samples from asteroids and comets. We could do experiments in space, not just observations, but even now our reach is limited to our own solar system. We can't send a probe to another star. The distances are too vast and the travel times too long with current technology. The nearest star system is 4.4 light-years away, and with our fastest spacecraft it would take tens of thousands of years to get there. But interstellar objects change the equation. They bring samples from other stellar systems right to our doorstep. If we can study them in detail, if we can eventually send spacecraft to intercept them and collect physical samples, we can do comparative planetology on a galactic scale without ever leaving our own solar neighborhood. This is why there's so much excitement in the planetary science community about these objects. They're not just curiosities, they're windows into the diversity of planetary systems across the galaxy, and they're our only practical way of studying that diversity with current technology. Let's talk about something that's not mentioned much in the press releases, but that's on every astronomer's mind: the possibility of fragmentation. Comets are fragile objects. They're loose aggregates of ice and rock and dust, held together by gravity and the weak structural strength of frozen ices. When a comet gets close to the sun, the heating isn't uniform. The side facing the sun heats up much more than the night side, creating thermal stresses. The sublimating ices create pressure beneath the surface, which can crack the nucleus. Sometimes these stresses become too much, and the comet breaks apart. Fragmentation events are dramatic and scientifically valuable because they expose fresh material from the interior of the nucleus that was previously hidden beneath the surface crust. We've observed numerous comets fragmenting in the past. Comet Shoemaker-Levy 9. When 9 famously broke into more than 20 pieces before slamming into Jupiter in 1994. Comet Linear disintegrated during its perihelion passage in 2000, providing a spectacular show but frustrating scientists who wanted to study the intact object. More recently, interstellar comet 2I Borisov underwent what appeared to be a fragmentation event or major outburst in March 2020, several months after its perihelion, brightening suddenly and changing its appearance. The question everyone's asking now is, will 3I Atlas hold together? An interstellar comet that spent millions of years in the cold of deep space might be more pristine and more volatile than solar system comets, which could make it more prone to fragmentation when suddenly exposed to intense solar radiation. On the other hand, the comet has already survived several months in the inner solar system as it approached perihelion, which suggests it has at least some structural integrity. The observations being conducted by the spacecraft fleet around perihelion will tell us whether the nucleus is fragmenting or remaining intact. If fragmentation is occurring, we should see sudden changes in brightness, alterations in the structure of the coma, possibly multiple separate comas if the fragments are large enough. By the time 3I Atlas emerges from solar conjunction in December and becomes visible from Earth again, we'll know whether we're tracking a single object or a dispersing cloud of fragments. And here's what they don't say in the papers. If 3I Atlas does fragment, we might lose our chance to fully characterize it. Fragmented comets are more difficult to study because the material is spread out over a larger volume of space, and the individual fragments may be too small and too faint to observe in detail. The total brightness might actually increase for a while after fragmentation, as fresh volatile ices are exposed and sublimate rapidly, but this elevated activity doesn't last long. The fragments quickly become faint and fade from view. On the other hand, fragmentation events provide unique insights into the interior composition and structure of comets, which we normally can't access. It's a trade-off, and there's nothing we can do to control which outcome happens. We're entirely at the mercy of the comet's own structural properties and the stresses imposed by solar heating. Now, before you start thinking this is all academic, that it doesn't matter to anyone except a few hundred astronomers who study comets for a living, let me tell you about the practical applications of this research. Understanding comets isn't just about satisfying curiosity. Comets have played a crucial role in Earth's history, delivering water and organic molecules to the young planet billions of years ago, possibly providing the chemical ingredients necessary for life to emerge. They've also posed risks. Cometary impacts can cause mass extinctions. We're pretty sure a comet or asteroid impact 66 million years ago wiped out the dinosaurs. On a shorter time scale, even small cometary fragments exploding in the atmosphere can cause significant damage, like the Tunguska event in 1908 that flattened 2,000 square kilometers of Siberian forest. Knowing how comets behave, how they fragment, what they're made of, this information feeds into our models of impact risk and planetary defense. If we ever need to deflect a comet that's on a collision course with Earth, we'll need to understand its structure and composition to choose the right method. Do you try to blow it up with a nuclear weapon, risking fragmentation that might turn one impactor into many? Or do you use a kinetic impactor to gently nudge it onto a different trajectory? The answer depends on what comets are made of and how they respond to stress, information we can only gather by studying them. There are also technological applications. The water and minerals locked up in comets represent potential resources for future space exploration. If humanity ever establishes permanent bases on the Moon or Mars, or builds habitats in orbit, we'll need sources of water, oxygen, and raw materials. Asteroids are closer and easier to reach, but but comets contain a higher fraction of volatiles, water ice, frozen carbon dioxide, ammonia, methane, that can be processed into rocket fuel and life support consumables. Mining comets is far beyond our current capabilities, but understanding their composition and structure is a necessary first step. And studying interstellar comets like 3I Atlas tells us whether comets from other stellar systems might be similar enough to our own that techniques developed for one could be applied to the other. This might sound far-fetched, but consider that private companies are already developing plans to mine asteroids, and several nations have expressed interest in establishing permanent human presence beyond Earth. The resource utilization question is going to become increasingly important in the coming decades. On a different note, let's consider what 3I Atlas means for our understanding of our place in the galaxy. For thousands of years, humans thought Earth was the center of the universe, that the sun and planets and stars revolved around us. Then we learned that Earth orbits the sun, not the other way around. Then we learned that the sun is just one star among hundreds of billions in the Milky Way galaxy. Then we learned that the Milky Way is just one galaxy among hundreds of billions in the observable universe. At each step, our cosmic significance diminished. We went from being the center of everything to being a tiny speck on a tiny planet orbiting an average star in an unremarkable galaxy. But there's another way to look at it. The discovery of exoplanets, planets orbiting other stars, has revealed that planetary systems are common, not rare. Most stars have planets. Many of those planets are rocky worlds like Earth, located in the habitable zone where liquid water could exist. The chemical building blocks of life, organic molecules, water, energy sources, appear to be common throughout the universe. And now, with the discovery of interstellar objects like 3I Atlas, we're learning that material is exchanged between stellar systems, that the galaxy is more interconnected than we thought. We're not isolated. We're part of a vast network of stellar systems that share material and possibly share chemistry. If life exists elsewhere in the galaxy, it might have emerged from the same kinds of processes that led to life on Earth, possibly even seeded by the same kinds of interstellar comets that are passing through both our systems. This doesn't make us more cosmically significant in the traditional sense, but it does suggest we're part of something larger, a galaxy-wide system of matter and energy exchange that's been operating for billions of years. That word interconnected is doing a lot of work there, and it's worth unpacking. When we talk about the galaxy being interconnected, we're not suggesting anything mystical or teleological. We're talking about physical processes, gravity, orbital dynamics, stellar evolution. Stars form in clusters from giant molecular clouds. As the cluster disperses over millions of years, gravitational interactions between stars can fling planets, comets, and asteroids out of their home systems, sending them wandering through interstellar space. Some of those objects will eventually encounter other stellar systems, where they might be captured into orbit or might pass through and continue on their way. Over billions of years, this process redistributes material throughout the galaxy. Every planetary system receives occasional visitors from other systems. In rare cases, those visitors might deliver organic molecules or even microbes, if any are present, to planets in the new system. This is the mechanism behind panspermia, the hypothesis that life might spread between worlds. Whether panspermia is actually happening, whether it's even possible for life to survive the journey between stars encased in a comet or asteroid, is still debated. But the physical mechanism for transporting material between stellar systems is real and well understood. 3I Atlas is living proof of that. The philosophical implications are profound. If material is constantly being exchanged between stellar systems, if comets rich in organic molecules are regularly visiting planets throughout the galaxy, then the emergence of life might not require a separate origin event in each system. life might have originated once, or a few times, in particularly favorable conditions, and then spread throughout the galaxy via interstellar objects. This doesn't answer the question of how life originated in the first place. That remains one of the deepest mysteries in science. But it changes the odds. If life only needs to emerge once in a billion star systems and can then spread to others, the galaxy might be teeming with life even if the initial emergence is extraordinarily rare. Alternatively, if interstellar objects deliver the same kinds of organic molecules to every planetary system, then every system starts with similar chemical ingredients, and life might emerge independently in many places using similar biochemistry. Either way, the detection and study of interstellar objects is directly relevant to one of the biggest questions humanity has ever asked. Are we alone? Stop and consider that. Right now, an object from another stellar system is passing through ours, and we're watching it with every instrument we can bring to bear. In a few weeks, it will be visible from Earth again, and telescopes around the world will track it until it fades from view. In a few months, we'll receive data from spacecraft that watched it during perihelion. Over the next year or two, scientists will analyze all that data, write papers, present their findings at conferences, debate interpretations, and gradually we'll build up a picture of what 3I Atlas is, where it might have come from, what it's made of, how it behaves. We'll compare it to Oumuamua and 2I Borisov, and to our own solar system comets. We'll refine our models of planetary system formation and evolution. We'll improve our estimates of how common interstellar objects are and what fraction of them might be comets versus asteroids versus something entirely unexpected. We'll learn about the chemistry of other stellar systems without ever leaving our own. And all of this comes from one small, icy object that's just passing through that will be gone in a few months and will never return. The question everyone's asking is what we'll find next. The Vera C. Rubin Observatory in Chile is scheduled to begin operations soon, and when it does, it will revolutionize the detection of interstellar objects. The observatory's telescope will photograph the entire visible sky every few nights, looking for anything that moves or changes. It's designed to find near-Earth asteroids that might pose an impact hazard, to track supernovae and other transient astronomical events, to map the structure of the galaxy. But it will also be incredibly effective at detecting interstellar objects. Current estimates, based on the 3 detections we've had so far, and the known sensitivity of the telescopes that found them, suggest Rubin might detect dozens of interstellar objects per year once it's fully operational. Imagine that. Instead of having a sample size of 3, we might have a sample size of hundreds within a decade. We'll be able to study the population statistically, determine what fraction are comets versus asteroids, measure their size distribution, analyze their compositions. We'll start to understand not just individual objects, but the interstellar object population as a whole. We'll be able to answer questions like, do interstellar objects preferentially come from certain directions in the galaxy? Are they more common in certain regions, like near stellar clusters or the galactic plane? Do their compositions vary systematically, suggesting different formation environments? This is the kind of data that transforms speculation into solid science. But here's the catch. Detection is only the first step. Once an interstellar object is detected, you have a limited window to study it before it passes through the solar system and disappears. For most of these objects, we'll only have a few weeks or months to gather data, just like with 3I Atlas. To really understand them, to answer the deeper questions about their composition and structure and origins, we need to do more than just observe them from a distance. We need to send spacecraft to intercept them, to fly alongside them, to sample them directly. This is technologically challenging because interstellar objects are moving fast, tens of kilometers per second, and they're on trajectories that don't match any planet's orbit. You can't just point a rocket at an interstellar object and chase it down. You need to launch on precisely the right trajectory at precisely the right time. And even then, you might not have enough fuel to match velocities. You'd have to settle for a high-speed flyby, perhaps deploying instrumented dust collectors to sample material from the coma as you zip past. But even a flyby would be scientifically invaluable. Close-up images would reveal the shape and surface features of the nucleus. Spectrometers could analyze the composition of the coma in far more detail than is possible from Earth. Dust collectors could capture particles for later analysis, potentially even returning them to Earth if the mission design allowed for it. Several space agencies and research groups have proposed missions to intercept interstellar objects, but none have been funded yet. The problem is the unpredictability. You can't plan a mission until you know an interstellar object is coming. And by the time you've detected it and calculated its trajectory, you usually don't have enough time to design, build, and launch a spacecraft to intercept it. The solution is to have a spacecraft ready to go, sitting on a launch pad or in storage, just waiting for a suitable target to be detected. This is called a rapid response mission, and it's a concept that's being actively discussed in the planetary science community. If we're going to take full advantage of the coming wave of interstellar object detections from Rubin and other next-generation survey telescopes, we need to have the infrastructure in place to launch interception missions on short notice. It's a significant investment, but the scientific payoff would be enormous. The first spacecraft to rendezvous with an interstellar object and return samples to Earth would revolutionize our understanding of planetary systems and might even reveal signs of exotic chemistry or biology from other stellar environments. Let me shift gears and talk about the cultural impact of these discoveries. When Oumuamua was detected in 2017, it made headlines around the world. People were fascinated by the idea of an interstellar visitor, something from beyond our solar system passing through our cosmic neighborhood. The speculation about its nature, was it a comet, an asteroid, something else, captured the public imagination. The controversial suggestion that it might be artificial, proposed by Harvard astronomer Avi Loeb, generated enormous media attention and debate. Some scientists praised Loeb for thinking outside the box and taking the artificial hypothesis seriously. Others criticized him for promoting speculation without sufficient evidence and for attracting undue attention to an idea that most researchers considered extremely unlikely. But regardless of where you stand on that debate, the fact is that Oumuamua got people talking about astronomy in a way that few other discoveries have in recent years. It made people aware that our solar system isn't isolated, that we receive visitors from the wider galaxy, that there are profound mysteries still waiting to be solved. That cultural impact matters. Public interest in science drives funding for research, inspires young people to pursue careers in science and engineering, and fosters a sense of wonder about the universe that enriches our collective experience as a species. 3I Atlas hasn't generated quite the same level of public attention, probably because it's more comet-like and less bizarre than Oumuamua. But among astronomers, the excitement level is just as high. Each interstellar object teaches us something new, and the fact that we're now detecting them regularly means this isn't a curiosity anymore. It's a field of study. There are researchers who are specializing in interstellar object science, who are developing techniques and models specifically for studying these bodies. There are conferences and workshops focused on interstellar objects. There are proposals for dedicated space missions. Within a decade, this might be one of the most active areas of planetary science, comparable to exoplanet research in its impact and its potential to answer fundamental questions about the universe. Think about what that means for our understanding of the cosmos. 50 years ago, we didn't know whether other stars had planets. The first exoplanet orbiting a sun-like star was discovered in 1995, just 30 years ago. Today we know of more than 5,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. We've learned that planets are common, that planetary systems come in an astonishing variety of architectures, and that Earth-like worlds are probably abundant throughout the galaxy. Exoplanet science went from non-existent to one of the hottest fields in astronomy in just a few decades. Interstellar object science is poised to follow a similar trajectory. We're at the very beginning of this field, with only 3 confirmed detections, but the pace of discovery is accelerating. In a few years, we might routinely observe interstellar objects, studying them with the same level of detail we currently apply to asteroids and comets in our own solar system. The insights we gain will complement and extend what we're learning from exoplanet research, giving us a more complete picture of how planetary systems form, evolve, and interact with each other across galactic scales. And yet, there's a bittersweet quality to all of this. Every interstellar object we detect represents a connection to a place we'll probably never visit. 3i Atlas might have formed around a star we can see in our night sky, or it might come from a star too faint or too distant for our telescopes to identify. We'll never know for certain. We can trace its trajectory backward through the galaxy, correcting for the motion of stars and the gravitational influence of the Milky Way's mass distribution, but the uncertainties grow larger the farther back in time we look. After a few million years, the error bars are so large that we can't pinpoint a specific star system as the comet's origin. We can only say it came from a particular region of the galaxy, a volume of space that might contain thousands or millions of stars. Any one of them could have been home, and 3i Atlas itself can't tell us. It doesn't carry a plaque or a radio transmitter identifying its origin. It's just a frozen relic, a piece of ice and rock that's been wandering the galaxy for millions of years, and we're lucky enough to catch a glimpse of it during the brief time it spends passing through our solar system. This is the fundamental limitation of studying interstellar objects. We can analyze what they're made of, how they behave, what processes shaped them, but we can't directly connect them to specific stellar systems. We're doing archaeology without knowing the sites of the civilizations we're studying. It's frustrating and tantalizing in equal measure, but it's also the only game in town, at least with current technology. Unless and until we develop faster-than-light travel or some other means of bridging interstellar distances quickly, interstellar objects are our only way of getting physical samples from other stellar systems. So we work with what we have. We observe. We measure. We analyze. We theorize. We squeeze every bit of information we can out of each interstellar visitor, knowing that it's our only chance to study material from its home system. And we hope that the next one, or the one after that, will reveal something unexpected, something that changes our understanding of how planets and stars and life fit together in the grand scheme of the cosmos. The final perspective on 3i Atlas, the one that ties everything together, is this. We're living through a pivotal moment in the history of astronomy. For thousands of years, humans have looked up at the stars and wondered what's out there. We've built increasingly sophisticated tools to study the universe, from Galileo's primitive telescope to the Hubble Space Telescope to the James Webb Space Telescope. We've sent robots to explore every planet in our solar system and some of the moons and asteroids. We've detected planets orbiting other stars and analyzed their atmospheres. We've learned that the universe is vast, almost beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars. And now, we're learning that the galaxy is more connected than we thought, that material flows between stellar systems, that we can study pieces of other worlds without leaving our own cosmic neighborhood. 3i Atlas, hurtling past the Sun at 125 million miles away while we scramble to observe it from every possible angle, represents both the enormity of what we've already learned and the vastness of what we still don't know. It's a reminder that despite all our advances, despite all our telescopes and spacecraft and theories, the universe still holds profound mysteries. We don't know where 3i Atlas came from. We don't know what it will do as it passes through perihelion. We don't know what surprises are lurking in the data that JUICE is recording right now and won't transmit for 4 more months. We don't know how many more interstellar objects are out there waiting to be discovered, or what they'll teach us when we find them. And that's exactly as it should be. The day we run out of mysteries, the day we think we understand everything, is the day science stops being exciting. 3i Atlas reminds us that we're still at the beginning of the journey, that there are still frontiers to explore and questions to answer, and that sometimes the most interesting discoveries come from places we never expected, like from beyond the stars themselves, carried to us on the backs of ancient wanderers who have spent millions of years crossing the darkness between